Today we shall study about dual nature of radiation and matter. In this article we shall study about effect of potential on photoelectric current. We vary the positive potential of plate A gradually and measure the resulting photoelectric current. As in the earlier figure, it is found that the photoelectric current increases with increase in accelerating positive potential. At some stage for a certain positive potential of plate A, all the emitted electrons are collected by the plate A and the photoelectric current becomes maximum or saturated. It was if we increase the accelerating potential of plate A further, the photocurrent does not increase. This maximum value of the photoelectric current is valid. The saturation current corresponds to the case when all the photoelectrons emitted by the emitter plate C reach the collector plate A. We now apply a negative retarding potential to the plate A with respect to the plate C and make it increasingly negative gradually. When the polarity is reversed, the electrons are repelled and only the most energetic electrons are able to reach the collector A. The photocurrent is found to decrease rapidly until it drops to zero at a certain sharply defined critical value of the negative potential V0 on the plate A. For a particular frequency of the incident radiation, the minimum negative or retarding potential V0 given to the plate A, for which the photocurrent stops or becomes zero, is called the cutoff or stopping potential. All the photoelectric currents, photoelectrons emitted from the metal do not have the same energy. Photoelectric current is zero when the stopping potential is sufficiently to repel even the most energetic photoelectrons with the maximum kinetic energy K maximum, so that K maximum our E V0. We can repeat this experiment with incident radiation of the same frequency but of higher intensity I2 and I3. We find that the saturation currents are found to be at higher values. We find that more electrons are being emitted per second proportion to the intensity of incident radiation, but the stopping potential remains the same as that for the incident radiation of intensity I as shown in the figure 1. Thus, for a given frequency of the incident radiation, the stopping potential is independent of its intensity. It depends on the light source and the emitter plate materials, but independent of intensity of incident radiation. Effect of frequency of incident radiation on stopping potential as shown in the figure 1. We obtain different values of stopping potential, but the same value of the saturation current for incident radiation of different frequency. The energy of the emitted electrons depends on the frequency of the incident radiation. The stopping potential is more negative for higher frequencies of incident radiation. In figure 1, V03, V02 and V greater than V01. If the frequencies are in the order of V3 is greater than V2 is greater than V1. This implies that greater is the frequency of incident light, greater is the maximum kinetic energy of the photoelectrons. We need greater retarding potential to stop them completely. We draw a graph between the stopping potential and frequency of incident radiation. Metal A, for metal A and metal B, B is greater than V naught. The observation have two implications. The maximum kinetic energy of photoelectrons vary linearly with the frequency of incident radiation, but is independent of its intensity. For a frequency nu of incident radiation lower than the cut-off frequency V naught, no photoelectric emission is possible even if the intensity is large. This minimum cut-off frequency V naught is called the threshold frequency. It is different for different metals. It gives different response to light of different wavelengths. For example, ultraviolet light gives rise to photoelectric effect in copper, while green or red light does not. Photoelectric effect and wave theory of light. In the wave picture, the absorption of energy by electron takes place continuously over the entire wavefront of the radiation. Since a large number of electrons absorb energy, the energy absorbed per electron per unit time turns out to be a small. Explicit calculation estimate that it can take hours or more for a single electron to pick up sufficient energy to overcome the work function and come out of the metal. This conclusion is again in a striking contrast to observation that the photoelectric emission is instantaneous. In short, the wave picture is unable to explain the most basic features of photoelectric emission. Now the Einstein photoelectric equation. Energy quantum radiation. In 1905, Albert Einstein proposed a radically new picture of electromagnetic radiation to explain photoelectric effect. In this picture, photoelectric emission does not take place by continuous absorption of energy from radiation. Radiation energy is built up of discrete units, the so-called quanta of energy radiation. Each quantum of radiant energy has energy h nu, where h is Planck constant and nu the frequency of light. In photoelectric effect, an electron absorbs a quantum of energy h nu of radiation. In this quantum of energy absorbed exceeds the minimum energy needed for the electron to escape from the metal surface. Work function phi naught. The electron is emitted with the maximum kinetic energy. So K maximum over h nu minus phi naught, that is called the Einstein photoelectric equation. The maximum kinetic energy of the emitted photoelectron is determined by the energy of each photon. We see the following observations. K maximum depends linearly on V nu and is dependent of intensity of radiation. The intensity of radiation that is proportional to the number of energy quanta per unit area per unit time is irrelevant to this basic process. Hence, there must be non-negative. Equation 1 implies that photoelectric emission is possible only if h nu is greater than phi naught or if nu is greater than nu naught, where nu naught per phi naught by h. Thus, there exists a threshold frequency nu naught per phi naught by h for the metal surface below which no photoelectric emission is possible. No matter how intense the incident radiation may be or how long it falls on the surface, the intensity of radiation is proportional to the number of energy quanta per unit time, per unit area, per unit time for nu is greater than nu s. Photoelectric current is proportional to intensity. In V naught बराबर h nu minus phi naught for nu is greater than equal to nu naught. H बराबर 6.62 गुना 10 to the power minus 34 joules second और nu naught बराबर और V naught बराबर h by e nu minus phi naught by e. The curve is a straight line drawn between nu naught and nu naught between Zinor and Nuke.